All right. Hello, everyone. We are back in Neumann algebras. My name is Fehmi Ekin Giritlioğlu. I go to Michigan State University. I'm a PhD student under Brant Nelson. Today, we're talking about the group measure space construction. So we have seen type 1n factors, which are n by n matrices. We have seen the separable type 1 infinity factor, which is bounded operators on L2 of n. We have seen type 2-1 factors, for example, the hyperfinite 2-1 factor or the free group factors. We have seen a type 2 infinity factor. In fact, we've told you that all type 2 infinity factors are a type 2-1 factor tensored with bound operators on L2 of n. So let's see some examples of type 3 factors. Now, type 3 factors are a little more difficult to construct. And I think the fastest way to go about it is the group measure space construction. So to construct the type 3 factor, what we're going to do is that we'll introduce a special case of cross products. We're going to cross product an abelian one Neumann algebra with a group. And the way I'd like to think about this is that we have our abelian one Neumann algebra, and then we'll add shufflers. These shufflers will shuffle the domain X and give us some non-commutativity. And smashing these two together is going to give us a one Neumann algebra. Now let's fill in the details. Example 4.3.16 in notes says that let X mu be a sigma finite measure space with a sigma algebra. Let gamma be a countable discrete group. Suppose there is a homomorphism alpha from gamma to the automorphism group of the one Neumann algebra L infinity x mu. We say that the automorphism is the set of normal star isomorphisms of this one Neumann algebra. Now, in this case, we call that alpha is an action of gamma on L infinity of x mu, and write gamma acts on L infinity of x mu. Now, when X is a standard measure space, what that means is that if X is Borel isomorphic to the unit interval with the Borel sigma algebra with Lebesgue measure plus up to countably many atoms, then the automorphisms of this one Neumann algebra we can actually write down. What this automorphism group consists of is measure class preserving measurable bijections phi from X to X. Now, what this means is that phi E, say we have measurable subset of X E, phi E is null if and only if E is mu null. If you have this condition, then phi is called a measure class preserving map. Now, if you take this map, we can turn it into an action on the automorphism group. Sorry, action on the one Neumann algebra. And how does this work? For F and L infinity function, the automorphism corresponding to phi would send F to F of phi inverse. For example, suppose our measure space is the points 0, 1, 2 with the sigma algebra, the power set of X with the counting measure. Z mod 3Z could be 2Z. Yes, I think it's 2Z. Z mod 2Z can act on L infinity of X with the counting measure by the nth element. This could be 0, 1, 2, the coset of 0, 1, 2. Is going to take f of point to f of point minus n. Just shuffling, just like I said, the shuffling. What's happening is that suppose we have a function taking 0 to 4, 1 to 5, 2 to 6. This is an L-infinity function in X. And when we put this function under the automorphism alpha 2, now we have shuffled. So 0 was being sent to 4, now it's being sent to 5. 1 was being sent to 5, now it got shuffled down, going to 6, and 2 is now going to 4. So, for example, f of 0 was 4. Now we have that alpha 2 of f of 0 is equal to f of negative 2, which is f of 1, and that should be 5. Like so. So just shuffling the domain. Now, we say that this action, so we want this action to be nice. And what does that mean? This action is free if for all function, L-infinity function, and for every group element of gamma, if we have that f times alpha g of h is giving me f of h for every h, so if nothing's happening, f is sending this h, whatever we apply to h, it's still being sent to h. This means that f is 0. So we have to have some freeness in the action, no trivial actions on some part of the set or anything. This action should be actually permuting something. And I want this permutation to be chaotic. So by chaotic, I mean ergodic. What that means is that for all g in the group, if alpha g of f is f, the only guy being sent to itself should be the identity element in L-infinity, namely the function 1. So if you're constant, under this automorphism, the only thing constant is f equals 1. Now, this can be thought of as x is being shuffled nicely. X does not have an invariant set. In standard spaces, in fact, this is a characterization. So if x is standard, this characterization is the same as saying for all. So if gamma e, meaning the set gx, g in gamma, x in e, define that. If this guy is e, then e has to be x. So the only invariant set should be x or null. X or e is null. And this quality is mu almost everywhere. Every equality sign for sets will be almost everywhere. So now we're going to define a linear operator. So remember back to the start when I said we're going to make a von Neumann algebra containing L-infinity and abelian von Neumann algebra, plus some shuffles. So how are we going to do this? We're going to have to represent both these shuffles and L-infinity together. And turns out the space we should be representing these operators on is L-infinity of gamma tensor L2 x mu. Now, this space might look complicated, and in fact, I'm going to say it's complicated. But how I like to think about this is matrices. So these are matrices whose components are in L2 of x mu, and these matrices are indexed by G. Okay. Now, how do we define this operator? How do we represent L-infinity? Suppose we have an element of the algebraic tensor. Let's worry about the closure later. So suppose we have an element in the algebraic tensor. Actually, this is not necessarily the algebraic tensor. This is in the completion because my indexing may not be finite. Anyway, suppose we have a generic element, sum over all the elements in the group, delta G. This delta G is the characteristic function 1G in L2 gamma. This guy is sending delta G tensor FG, where this is an element in L2 of X mu. What's going to happen is that it's going to shuffle the Gth guy with alpha G inverse F. Okay, what's happening here? Let us see where it's sending this element. This element is being sent to delta E tensor alpha E inverse F, Fe. Well, alpha E is nothing, where E is the identity element of the group. If you have an automorphism, the identity element's automorphism is just going to be nothing. It's going to be identity. So this guy is delta E tensor F times F. Okay, so what happened here? What happened here was that an element F in L infinity, we're trying to represent L infinity, to the delta E tensor element is just acting as multiplication on the second part of the tensor. But what's happening here on the Gth element? Well, these Gth elements are representing shuffled counterparts. So when we have that, delta G, Fg is being sent to alpha G inverse F. So it's going to be sent to, nothing happens to the first coordinate, but the second guy, I have to shuffle it first, Fg. What this delta G records is that this is what's going to happen to a G shuffled function. If you're G shuffled, for your unshuffled F to act on the shuffled guy, you have to shuffle it first. So to act as a multiplication on F of G, we have to shuffle it also. That's how I like to think about it. So my behavior as being a pointwise multiplication operator, the usual L infinity, a usual element in L infinity being a multiplication operator, is still a multiplication, but it has to remember that it's acting on a shuffled function by being shuffled itself. Okay. Now we continue with how we represent L of G. Sorry, how we represent the G. So we have successfully represented L infinity. Now, how are we going to represent the groups, the shufflers? Now, first we have to take care of some formalities. For example, I'm claiming that this represents L infinity, but this is actually representation. Are the images of these guys actually bounded operators? So exercise 4.3.11 takes care of that. This says that this pi alpha, the representation of L infinity corresponding to the action alpha from L infinity of X mu to bounded operators on this Hilbert space that we talked about is, honest to God, a normal unidal injective star homomorphism. So it takes this guy, embeds it inside. So all these details are in exercise 4.3.11. So a priori, we don't know if this mapping here is in fact bounded. We're working with bounded operators. Turns out it is, and everything's fine. Now for G and gamma, let's represent the group elements, the shufflers. What they do is they take a generic element, delta H tensor FH, a sum on all elements into a group, and they send it to delta GH. So what happened is that everyone got shuffled. So if you were delta E, you are now, so times 1, you are now sent to delta G times 1. You got shuffled. Well, actually, these are also shufflers, but that's for later. So now how do these two representations act with each other? How do they behave? So exercise 4.3.11, part C says that if you have lambda G, pi alpha of F, and lambda G inverse, this is also lambda G star. So this conjugation gives you pi alpha of F. So we have this nice conjugation relation. Now, what does this help us do? If I have some words written as such, what I can do is I can pass this on to here. How so? So this is equal to what? G. I'm going to make H here. And then we have pi alpha of F and the H. Using the commutation relation, using the conjugation relation here, we're going to have this happening. So this should be A alpha. And I think we are missing a subscript. This should be alpha G. So in our case, that will be alpha H inverse. So what happened here is that we have made this, lambda pi lambda into just lambda pi or pi lambda. You could flip this. Apparently what we chose later on was that we could write the star algebra generated by the representation of L infinity and gamma. We can make every complicated word into just a sum of pi and lambda. Once again, using this commutation relation, I can turn every big word into just a word of length 2 of pi first, lambda second, or lambda first, pi next. Okay. So let's record this. The star algebra generated by these two guys it is just this sum right here. Now, these coefficients, you could have maybe like 5 here, but that 5 could be absorbed into the function itself. So we just put it inside the function. Now let's look at this. The star algebra generated by these two guys can be written as the sum, finite sum, because just the star algebra, we're not taking the closure yet, is going to be the sum of pi alpha fj and lambda gj, where d is a natural number and fj are just functions in infinity and gj are elements of the group. Now notice this contains the unit, namely just lambda of e is the unit of b of h, where our h was this tensor Hilbert space. If you have a unitable star subalgebra, what can we do? Take its closure and get a Neumann algebra. And what's the coolest way to take a closure? take the double commutant. So when we take the double commutant of this star subalgebra of B of these tensors, we get the cross product of L infinity by this group. So we have L infinity represented as such. We have our shufflers represented as such. Take its closure. This is called the cross product of L infinity by gamma. This cross product and this process is called the group measure space construction. Okay. Now we've talked about freeness and ergodicity. Let's remind what they are. Freeness meant things are being shuffled, and ergodic meant there is no set that was invariant other than the entire set. Now, one more concept is probability measure preserving. Before that, exercise 4.1.5 says that if alpha is free and ergodic, then the von Neumann algebra given to us by the group measure space construction is a factor. Interesting. The ergodicity and freeness, this shuffling conditions, if you make necessary the conditions that our shuffles have to actually be shuffles, they can't leave something invariant, you get a factor. You get the non-commutativity is enough to obtain a factor. This is 1940 Murray and von Neumann. Now, what is probability measure preserving? If you like 2-1 factors, you're going to work with probability measure preserving actions. If for all g and gamma, and for all functions, if you shuffle the function and take the integral, it has to stay constant. Also, you also need to have that mu is a probability measure. So if mu is a probability measure and your shuffles aren't changing the integral of the function, then alpha is called a probability measure preserving action. Okay. Now, recall that we talked about standard measures. So the measure spaces that are Borel isomorphic to the interval with Lebesgue measure plus maybe some atoms. From now on, we're going to only work with these kinds of measures. Is my mic working okay? My audio is showing a little.
We can hear you okay. I can at least.
Okay, thank you. So we do not want to work with what I'll call bad measure spaces. We're just going to work with standard measure spaces. I'll give an example. For example, if you have real numbers with the sigma algebra, the power set of R, so all subsets, and as the measure, take the counting measure, this guy is non-standard. This guy's huge. So I don't want huge spaces like this. Now, we'll assume all measures are standard. Now back to gamma acting on L infinity of x mu. Goals notes, they recommend that we think of this action, this cross product, as a von Neumann algebra containing the abelian von Neumann algebra L infinity x mu and the group von Neumann algebra with commutation relations given by what we talked about, this conjugation identity. Now, suppose alpha is free, ergodic, and probability measure preserving. This would be your 2-1 factor or 1n factor setting. This function, suggestively denoted tau, from the cross product to C, defined by tau x, to x evaluated at delta E tensor 1, product delta E tensor 1 is a trace. Now, what is this function? What this function is looking at is, so say you have an element in the von Neumann algebra, in the cross product. So some element in cross product. What we're looking at is, what does x do to a non-shuffled one, the non-shuffled identity, and then looks at the component that is still unshuffled one. For example, if you have, so this is, if you think of the Hilbert space, the tensor Hilbert space we defined as matrices indexed by the group gamma, this is literally the trace, the diagonal. This is summing up the diagonal, technically. So if you have an element as such, the sum j from 0, I took it from 0, you'll see why, to up to d of pi alpha fj lambda gj. This is a special element. I took it as just a finite sum, where g0 is just the identity. Then what we're going to get as tau x is just the integral of f0 d mu, the non-shuffling part. Now, this turns out to be a trace, right? So when you have a trace like this, we get that our von Neumann algebra is a factor. Is a finite factor. What does that mean? It is either type 1n or 2-1. Okay, but we talked about getting type 3 factors. How does that happen? If you let go of probability measure preserving, then we can get all types of factors. For example, if you want a type 1n factor, we can take the cross product of L infinity of modulo n integers with the counting measure. So let's write that down. So we have cosine of 0, cosine of 1, up to cosine of n minus 1 with the counting measure. And my sigma algebra is all subsets. If you take the cross product with z mod nz acting as the shuffle we talked about before, this shuffle right here, where I gave an example of, like this. How do we write that down? We write that down as such. So alpha g of f dot is f of dot minus g. So your function, you have points, just get shuffled. This gives us, this doesn't give us M and C. It does give us M and C. Never mind. This gives us n by n matrices on C. Now contrast this with the fact that the von Neumann algebra, the group von Neumann algebra of this guy is not n by n matrices. Why is that? This group is not ICC, infinite conjugacy class. So we cannot have a factor. But when you take this cross product, you get a factor. So contrast right there between the group von Neumann algebra and the cross product. Now, how to get a type 1 infinity factor? You take, instead of an n element cyclic group, you take natural numbers. Sorry, you take whole integers. So when you take the integers as your probability space with sigma algebra, everything, all subsets, you take that cross product with integers with the same action, and you get the type I infinity factor given by boundary operators on L2 of C, the separable type I infinity factor. Now let's look at a type 2-1 factor. If you have L infinity of the torus, the circle. And then you take your measure as arc length. And then you act on it with integers as such. So you rotate by e to the negative ig. Now, what this is an irrational rotation. There's no pi, so it's an irrational rotation. This gives you the hyperfinite 2-1 factor. So if you have, suppose there's this set, you shuffle it, now it's this set. It never comes back to itself. It's always a bit tainted. That's what gives you the ergodicity and freeness. And you get the 2-1 factor, the hyperfinite 2-1 factor. Now, type 2 infinity, how do we get type 2 infinity? You can say, oh, just tensor it with this guy. That's exactly what we're going to do. Now, my measure space is torus times z with arc length times the counting measure. And we're going to take the cross product with z times z. How is this going to happen? We're going to have our automorphism of a group element be, well, first coordinate is being acted on like the first, the rotation map, and the second is going to be just like the first action of integers. And this gives you a type 2 infinity factor. In fact, it gives you R tensor B of alto Z. Now, for the moment, hopefully some of us have been waiting for, how do we make a type 3 factor? Okay, let's do it. Our infinity space is going to be real numbers with the Lebesgue measure. Okay, simple so far. And our action is going to be the action of positive rationals with multiplication and rationals with plus, the direct product of them. And how is this action happening? The GH automorphism on F is going to be F of point minus H divided by G. So what's happening here? This is called the AX plus B group with rationals. It's acting on real numbers. What's happening is that this B part here is moving. So suppose this is my real numbers. This B part here is moving this guy into here. And this A part is making it smaller or larger. So what's happening is that if I have, say, 1/2, it's going to take this guy and halve it. So suppose we have some origin here. This halves the set, say, like this. So now if you notice, this B here is not changing the measure of the set, since Lebesgue measure is translation invariant. But this A part is changing the measure of the set. It's enlarging it, it's making it smaller. This is what gives us the type 3 factor, basically. What you can do is show that you can send every set to any set you want by these shuffles, basically. Since we have access to this enlargement, what we can show is that every single, so remember our cross product was a combination of F and G, sorry, combination of L infinity and G. So say for all projections, so for all non-null projections, pi alpha of 1e is going to be Murray von Neumann equivalent, if you remember from equivalence of projections, to 1 of f. So let's have 2 of them. So every single projection in L infinity is going to be equivalent because we can enlarge everything. This is not easy to prove. And if you ask me right now, I couldn't do it. Right now, to write it down, I couldn't do it. Now, luckily, we don't have to do all these, and theorems have been proven by, once again, Murray and von Neumann in 1940 to tell you instantly when our factor is type 1 and 1 infinity, 2, 1, 2 infinity, 3. So suppose we have an ergodic and free action. Let's denote M, the cross product of L infinity of X and gamma. Then we're going to have a type 1n von Neumann algebra if our measure space is just n many atoms. If you have just n atoms and we're shuffling them, that gives us n by n matrices. Type 1 infinity, if we have countably many atoms and you're shuffling them, you get the separable type infinity factor. And then M is type 2, 1 if there is, we can find a measure. So remember, we first asked to have a 2, 1 or IN factor. We asked for PMP, probability measure preserving. What this is saying is that if there exists a measure such that the action becomes probability measure preserving, that means, and of course, X is not type 1, then we get a 2, 1 factor. Now, what this is saying is we have a special trace. Special meaning, so we have a trace. Let's talk about trace first. We have a trace that sends X to Q integrate what you're going to do is we had delta E, tensor 1, tensor 1. But we used to integrate this with mu. So instead of mu, we're going to integrate it with nu. And since with nu, this guy is probability measure preserving, we're going to have a trace. Now, why is it special? It's special because if you have a traceable Neumann algebra in your cross product, I haven't told you it doesn't have to look like taking it against an unshuffled vector. So this is more than saying we have a trace. This is more than saying our trace is looking at an unshuffled guy and see what our elements are doing to it and integrating it with some kind of measure. And not all traces are going to look like that in the von Neumann algebra. We might have, for example, if you have, actually, never mind. But not all traces have to look like this with respect to some measure. Or hopefully, but technically, luckily, they have proven that we have to have it. For example, in the type 3 case, we have some big issues with this, some open problems and such. Now, how about to infinity? Now, we required that this measure be probability. If you remove that, we don't want probability, but we just want measure preserving. And of course, not type 1, we get a to infinity factor. And if none of these work, then M is type 3. Okay. Now, let's ask, okay, can we get every factor with this group measure space construction? Now, this is a very difficult problem. Luckily, it has been solved. Theorem by Voiculescu in 1995. Voiculescu says that for any natural number between 2, so larger than 2, the free group factor, L of Fn, cannot be obtained by the group measure space construction. Interesting. How was this shown? Voiculescu showed that the free group factor doesn't contain what's called a Cartan subalgebra. But in every single group measure space construction, we have a Cartan subalgebra. This has been known since 1940, they say. I think so, yeah. Namely, the copy of L infinity of X mu. Now, what is a Cartan subalgebra? It's a Cartan subalgebra. So let M be a von Neumann algebra. Let A be maximal. So let A containing M be a maximal abelian von Neumann subalgebra. So it has the unit and it's closed in sigma weak operator topology. It's a star subalgebra. A is called Cartan. A is regular. Now, what does that mean? Regular. A is regular. We define the normalizers set. This is all unitaries in unitaries of M, such that UA U star is A, or contained in. I forgot. I think it's A. So the normalizers are you conjugate the subalgebra, and you still get A back. These are called the normalizers of A. Now, regularity, if you take the satisfies, so this generates the von Neumann algebra. So the unitaries that normalize A are enough to generate the entire von Neumann algebra. This is called Cartan. And Voiculescu in 1995, I think using free probability, showed that the free group factors don't contain any Cartan subalgebra. So if anytime in the wild you think, okay, I have to show that what I have is not a cross product, maybe this is a way to go. So theorem proved, I think Murray and von Neumann. That's what my source is in my second monitor is saying. The source is Hagerup's third talk at masterclass on von Neumann algebras and group actions. So they say that every group measure space construction, let's say this, cross product, has a maximal abelian subalgebra. And my source is not saying if it's Cartan or not, unfortunately. So undetermined time theorem, this Monza is Cartan. In fact, and this subalgebra is indeed pi A of L3. Now, since we have some more time, I'll talk about a remarkable theorem by Feldman and Moore. Every separable von Neumann algebra with a Cartan subalgebra can be witnessed as a von Neumann algebra coming from an equivalence relation. Now, this is almost, I'm going to be very naive here, can almost be thought as this cross product where the action doesn't necessarily have to be free. So one remarkable thing that has been noticed is that when you have an action, so you have an action on L-infinity of x mu, all the data of shuffles are contained in the equivalence relation R in x times x given by if and only if there exists g, gx is 1. Now, so this remarkable thing is that you can forget the group and just look at the equivalence relation and just look at shuffles that obey the equivalence relation. So what we look at is one can get all the info from the group of automorphisms. So Borel automorphisms of x such that phi x is related to y. So forget the group, just look at every single shuffle such that my shuffles are landing in things that G's could have already landed them in. So just if you can make any map where your map is borrowed from the group, then these maps are enough to construct the von Neumann algebra. Okay. And that's all I have to say for today. I will stop recording.